Hi, good afternoon, everyone. Let's take a moment for the participants to settle down. All right, really, let's get started. Welcome to the ImmPort 2023 webinar series. My name is Sanchita Bhattacharya. I'm the science program lead for ImmPort. On behalf of ImmPort team, I extend a warm welcome to all of you and thank you for joining us today. And I'll be moderating this session. In this webinar, we have the privilege of hosting two great speakers, Dr. Guanming Wu and Dr. Oliver He. Earlier this year, they published an impressive paper harnessing vaccine data sets from ImmPort. Today, we will have the opportunity to learn from them about the development of VIGET, an innovative web portal, followed by a live demo showcasing some of its major features and the real-world applications. So before we begin, I would like to cover a few housekeeping items. There will be two presentations and a short live demo, followed by a Q&A after each presentation. Please feel free to post your questions in the Q&A window anytime during the session. And then we will take a few questions live, and our team will also provide answers via text. So based on previous requests, today's webinar will be recorded for future access. So if you have colleagues who were unable to attend, they will have the opportunity to watch the recording at a later time on the ImmPort website. So without further ado, let's delve into the webinar titled VIGET, a web portal for the study of vaccine-induced host responses based on reactome pathways and ImmPort data. Our first speaker is Dr. Guanming Wu. Dr. Wu is an associate professor at Oregon Health and Science University with over 20 years of experience in the bioinformatics and computational biology field. He has focused on pathway and network-based data modeling, analysis, and visualization. He is also a co-PI of the Reactome project. So with that, I turn over to Dr. Wu.
Thank you.
Stop sharing.
Yeah, can you share my screen? Let me adjust my screen a little bit.
Yeah, it looks good.
Yeah, it's good. So first, we'd like to thank the Secretary and the ImmPort team to give us a great opportunity to present a web app we have developed during the past several years with the grant from the ImmPort project. The web portal we call the VIGET. So I'm not exactly sure how we should pronounce it, but just see VIGET. So it is for vaccine response gene expression analysis tool based on Reactome ImmPort. So it basically is a web-based tool for study of vaccine-induced host responses based on Reactome pathway and ImmPort data. So mainly for gene expression data. So our talk will be divided into 4 parts. First, I will use several slides to give a quick introduction about the project. After that, I will talk about how VIGET was developed and how we collect data from ImmPort and from GO. And then the software architecture and some of the major analysis and visualization features we have developed at VIGET. After that, I will do a live demo to demonstrate how VIGET works on the live. So after the demo, Oliver will present some application cases to show how VIGET can be used for some systematic vaccine post-response data analysis. So VIGET was designed as a web-based software tool for researchers to conduct gene expression-based vaccine host response study. So we use vaccine autology and some other related biological ontologies developed at Oliver's group to systematically process the vaccine response data collected at input data. Based on the input data, we then develop scripts to download the data from GO. After that, we process this data and load them into the VIGET stack and server. So we then develop the user interface based on JavaScript for researchers to conduct the differential gene expression data analysis for host response data. So for data analysis, VIGET use Reactome for pass-level network-based gene expression data analysis and visualization. Just in case if you are not exactly sure what Reactome is the most comprehensive open source, open access biological pathway knowledge base. So it is widely used in the community for pathway data analysis and visualization. Reactome has a quarterly release schedule. The current release is release 85. It was released about 3 months ago. The content in Reactome is manually curated by Reactome's internal curators. Most of them have PhD degrees in biology. The first curation target species is a human. So the latest release, which is release 85, contains over 14,000 complexes, which are annotated into over 14,000 directions. All these regions are organized into 2,629 pathways. These pathways cover over 50% of total human protein coding gene, something like over 11,000. So these annotations are supported by over 36,000 parameter indexed papers, which are manually screened by Reactome curators. In addition to manually curate pathways, region and complex in human, Reactome also use supporting gene or surrogate mappings to project human pathways to other non-human model organisms such as mouse, worm, fly, zebrafish, and the yeast. So by combining the data related tools together into a single web tool, we hope to provide research a very simple biology intuitive tool to conduct the vaccine response analysis using gene expression data. So then the first question is, how did we collect the host response gene expression data for vaccines based on input and GO? To do that, we developed a semi-automatic workflow as shown here after downloading the input MySQL database to generate a data file using both scripts and menu curation. So basically, we query the downloaded input database first to collect all so-called EXP sample object and their related information with the focus on subjects having information or immune exposure with gene expression data. So after that, in order to focus on data on vaccination study, we removed rows having passive genes as exposure materials, which do not have the vaccine ontology annotated vaccine identifier. Further, we remove rows for DNA sequence data because our focus is on mRNA expression data. After this 3 filtering process, we got 5,817 samples out of 11,692 originally collected input database. So to collect the gene expression data collected from GO, so we mapped GSM accession number to GSE and GPL. Some of the GSM code may be referred by more than one GSE code. So to avoid the duplication, we did some kind of automatic duplication remove redundant GSE accessions. Since our focus is really on DNA microarray-based gene expression data, so we also remove two platforms. One is the RNA-seq, another one is for peptide array. And then we also check each downloaded GSC data sets and remove one called GSC 41080, which doesn't have the kind of matches data. So after that, we write a simple R script to batch download and batch analysis using PC to check the batch effect. And say, since our focus is merely to do the pathway, the batch gene expression analysis, so we also remove gene expression. We also remove GSCs having only one time point. And the same, we also remove this one specific data because basically we cannot really express a batch effect based on our analysis, based on import the code and actually also check the GL. But we actually have not checked the original paper. And then we remove another data set, GSC 2121, which has really two sparse data. After that, in order to support our frontline, we normalize the heads and then convert all these tiny units into days. So based on this one, based on this meta file, we generate a single gene expression matrix file and put this file into a backend for the web application. So in total, the final data set covers 21 vaccines based on vaccine name or 20 based on vaccine term IDs, 28 input studies, 4,859 biosamples that were collected in 24 GSC data sets and conducted using 12 GPL platforms. The sample in the dataset were annotated for 7 races, 4 cell types, 184 cell subtypes, with ages ranging from 0 to 9 years, and vaccination days from -7 days to 84 days. So based on our to the best of our knowledge, so we have not really collected any RNA-seq-based data yet, but we believe this is a really comprehensive large data set for studying vaccine response in a systematic way. So this 21 vaccines can also be further classified based on vaccine ontology, as you can see here in this table. As you can see here also, because of the wide use of influenza vaccines, it is not unexpected that we see the dominant majority of studies are for influenza vaccine. So as you can see, actually you cannot really see, so 68 of 4,859 samples are actually annotated in 16 input studies for influenza vaccine, and the yellow fever virus vaccine has the second largest samples. 482 GSM samples annotated in 4 studies. Since the gene expression data was collected from multiple studies and connected by multiple platforms, so batch effect was expected, as you can see here in this human plot. So we tried a batch collection algorithm used in single-cell RNA-seq data analysis called BBKAN to collect the batch effects for GPL and also for GSC. As you can see here, BBKAN removed the batch effects quite efficiently, but some of the batch effects still exist. So for example, like this GPL 105558, which is colored as this cyan can. You can see a lot of samples coming from this GPM. They are still kind of separate from other samples, which basically means they are still batch effect existing even after this batch collection. But for our web-based application, we annotated the gene expression data with batch information directly on GSC and the batch analysis results, allowing users to load. We use the original data by integrating the batch annotation directly in the analysis data model, in the gene expression statistical model, which actually is the lemma we used our backend. So basically, to handle this batch effect, we annotate all these samples directly without delect the batch correction. So we also checked the distribution of gene expression values for individual vaccines and found that the majority of vaccines collected in our data set have similar distribution, where expression value between 25% and 75% have fallen in the range between somewhere around the 3 and somewhere around the 9, except 2 includes the vaccine. One is this one, and another one is this one. So these two vaccines having themselves have very similar distribution, but much wider than other vaccine. The interquartile range is between 3 and 130, with many outliers having high expression values, as you can see here. So with this slide, I'd like to switch the gear to the actual VIGET web application itself. To implement this web application, we adopted a two-tiered software architecture composed of 3 components. The front-end JavaScript component was implemented with this Vue.js, which is one of the most popular JavaScript framework currently in the market. At the server side, we have two components. One is a Java-based Spring model will control app component, which provide a RESTful API for the front end, and another one is R-based component, which runs lemma, the statistical model we use for the differential integration analysis into this model. In order to do password-based and network-based data analysis visualization from this Java component, we leverage 3 RESTful APIs provided by Reactome. One is called analysis service for password enrichment analysis, content service for pathway analysis results visualization, and also functional intelligence service for network-based data analysis visualization. So the VIGET itself provides a 2-step protocols for users to conduct differential gene expression analysis using graph user interface. So step one here is designed for users to first select the patients for differential gene expression analysis. Users can first select the vaccines as listed here, and then select the input studies platform used for all these studies, and then day 0 definition and notate the input. And after that, they can choose the gender, age, race, and cell type and subtypes. After that, they go to the second step. The second step basically is designed to choose 2 groups for differential gene expression analysis. In this second step, the user can also choose some confounding variables, which will be passed into the backend lemma model for differential gene expression analysis. After that, the user can just click this analyze button and do differential gene expression analysis on the fly using our web app. So this is the gene expression analysis widget visualization. And as you can see, there are 2 views displayed in this widget. The first one is a JavaScript called interactive volcano plot. The second one is a table showing all these genes, the results come from the differential expression analysis. So the user can do all this zoom in, zoom out as kind of standard interactive plot. And then in this table, they can filter based on gene name and then log for the change p-value and the p-values. So in my live demo, I actually show how this looks like. So based on this list of genes, so the user have to select the threshold, so they can choose a set of significant genes for pathway analysis and then also for network analysis. For pathway analysis, they can just click this button and then the pathway analysis results will be displayed here. So similar for gene expression analysis view, this will also provide 2 widgets. The first one is a scatter plot, and the second one is the table view. So in the scatter plot, each dot is a reactome pathway. They are colored based on the annotated top level pathway in Reactome database. So for example, like cell cycle, so we have annotated multiple several pathways in the cell cycle. They are all colored in the same color. And to facilitate comparison analysis, this will also fix the order of all these pathways annotated database, which is about 2,500. And based on original pathway hierarchical structure annotated in Reactome. And in this table, the results come from pathway enrichment as from Reactome. So the user can click each link and go to the direct analysis results at the Reactome website. They can also do some kind of filtering based on p-values and FDR values, and also based on pathway name. So the pathway widget also provides a link called open in Reactome. If the user clicks this link, so it will bring the user to browse the analysis results collected inside the Reactome's website. Here, this so-called Illinois map. This is a detailed heuristic view for all Reactome pathways. As you can see here in this view, each section here, something like the immune system, is a top-level pathway in the database. And the pathways annotated in each top-level pathways are rendered either in a hierarchical way or are just a flattened list as shown here. So from this, the user can easily see. So for example, like there's strong signal in immune system pathway and also some pathways in this topic called cellular response to stimulus, actually significantly enriched for whatever gene list submitted to pathway data analysis. So proteins are genes are organized in pathway for better understanding their biological function. But sometimes because of the difficulty of setting the pathway boundaries and learning the crosstalk between pathways. So network-based visualization are preferred to learn functional relationship among genes or proteins. So the VIGET uses the random functional interaction network to construct function interaction subnetwork for the selected significant genes. So this network will, as shown here, offers user to study potential functional relationships among genes having significant differential expressed data between two groups. So from here, the user can really see how these genes are functionally related to each other. So one of the major features of the VIGET is a comparison between two or more analyses. So for example, using VIGET a two analysis comparison between 3 time points. Time point is 0, 3, and 7. So for example, they can do first analysis between 3 days versus 0 days after vaccination, another analysis between 7 days versus 3 days after vaccination. After that, they can try to compare the analysis results between these two analysis and visualize the analysis at 3 different levels, at gene levels, at pathway levels, and also at the network levels. So this slide shows a screenshot showing the visualization of comparison of the pathway analysis results between these 2 time points, like 7 days and 3 days. So as you can see here, this is just an example. So from here, we can see interference signaling has a much stronger response at day 7 than at day 3 based on their p-values. So Oliver actually will present some actual application examples in more details after my lab demonstration. So before I do a live demonstration, I'd like to show some links. Currently, this web app is deployed at this website hosted at the VIGET web server at the University of Michigan. So this is URL. So that we have also published a paper to describe this web portal in Frontier in Immunology several months ago. So if you like to check out, you can download it. So it is open access. So you can check it out for text paper. And the code the code behind this web app is hosted at the two GitHub repositories. The first one is the web front end, and this is the server-side code. The web front end, as I said, is JavaScript-based. The server side is Java-based. And the data for the web app actually has been released. You can go to the, you can just click this and we provide the data at a certain bundle, and there are two files. The first one is the actual expression matrix file. The second one is the, the first one is the meta file. The second one is the single G expression matrix file. So all data on the software and the source code are open for both academic and commercial use. So we try to use least constrained license for both academic and industry or commercial use. So before I do demo, do you have any questions? Wait to answer now. Okay, so let me bring my web browser first. Okay, so how can I actually can you see my screen?
Yes.
Okay, so it's the web browser, right? So this so this is our website. If you go to this VIGET.Balinnet.org, so you can see this is the web front end. So as I said before, this is a two-step process to set up analysis. The first one is try to filter biosamples. So in this first step, so we listed all vaccines in our database as a hierarchical way follow vaccine ontologies hierarchical structure. So each vaccine actually is linked. So you can click to go to the website called AutoB to look at the detailed information about this specific vaccine. So the website hosted at the Holiday School at the University of Michigan. So then at this user interface, you can click it to select the vaccine I want to do analysis. So after you selected this, for example, flu vaccine, so then a list of ImmPort studies annotated for this flu vaccine will be listed. So in this case, we got 3 studies. Study 269, 270, and 61. So each study is hyperlinked to ImmPort. So like click this, you can go to ImmPort's website and look at the detailed information about this specific study. So in this case, I will just choose SDY269 just for demo purpose. So then under this study, so there are multiple platforms have been annotated. So, but in this specific case, we have only got 2. So for demo purpose, I will choose both of them. After choose this platform, so then the next section is about so-called day zero definition. It basically is annotation come from ImmPort. So it is called is the time of enrollment or time of initial vaccine administration. So in this case, I just choose both of them, and then you can also choose gender. So like female, male. So in this case, I just select all. And sometimes you will see multiple age ranges, but in this case, it's just between 0 and 47 years old. And then, so this, if there's only one choice, so that it will be automatically selected. Otherwise, you will see multiple choices. And then come to race. And in this case, the race will have this issue bracket for American white. So for my purpose, my demo purpose, I just select all. And from here, you can see all this cell type and all the subtype. So you can see there are multiple related. So we annotated all the cell type and subtype and put information here. So for this demo, I will just choose PBMC. And after that, so you just click next. So go to next is really to set up analysis. And to set up analysis, we wanted to choose samples for group 1 and group 2. So for this one, for this analysis, what I wanted to do is try to select the samples at the time 0 as group 1, samples at the time day 3 as 26, 26 samples at the time 3 as group 2. So how to do that? Just click this and drag drop here, and then click this and drag drop here. So basically means like 3 days for group 2, 0 days for group 1. And after that, for the actual linear regression model or lemma model, so you can choose multiple confounding variables. But some of them are actually default checked because we believe by check off it will give us better results. And for the display purpose, it will be also suggested to name the analysis results. So in this case, I will just call this 3 versus 0. So after that, you just click this analyze. So that all this information will be sent back to the server and get the results. And as shown here, so this is the expression analysis results. As I said in my presentation, so this is a volcano plot. This is a paper display view. So this, as you can see here, so this is interactive. So when you put a mouse here, so you can see some kind of detailed information. So for example, this is IF 103. So it has a negative log for the change, which means it has a high expression value in group 0, which is basically day 0. And the color actually is based on the default selection. And this is some blue dots for significant genes and the gray dots for not significant genes based on this line. And as interactive widgets, so you can do zoom in, zoom out, so something like that. You can do really zoom in, zoom out, do whatever you like. And after that, if you don't want to do anything, you can just set back and do a lot of interactive visualization. And the plot itself can actually be downloaded. You can click this, download the plot as a PNG. And with this table, you actually can do a filtering based on gene name. So for example, if I just wanted to see interleukin-related protein, so the genes, so you can enter IL, so there are the genes contain IL will be listed. So then you can actually come back. And then you can also change the log twofold and also change the p-value. So if you change p-value, so the actual display will be automatically adjusted based on your p-value. So for demo purpose, I choose 0.05. So if everything works fine, if you think there are actually a list of genes that are really significant, so then you can click this path analysis. So before I click this, I also like to point out you can also download the results into external CSV file. So you can do further analysis for whatever algorithm or approach you like. So if you click a path analysis, the list of selected significant genes will be submitted to Reactome's web-based analysis feature and come back some results like this. So this one as I said, each dot actually is a random pathway. So here, let me just zoom in this a little bit. So they are colored based on all these list of top level pathway. So just to try to make it more sense. So this is all these top level, about 25 top level pathways organized in Reactome. So in this view, you basically can just click this. So for example, because we're talking about the immune response, so we can just double click this. So everything will be focused on immune system. And then if you put the mouse here, so you can see what actually pathway this is. For example, this is signaling by interleukin. So it's top level pathway in the immune system. And it has a stable identifier actually come from Reactome, and its p-value is 4.86 E-6. And this is basically this scatter plot view. So the dot, they are arranged based on the actual pathway stretch, pathway annotation in Reactome. So they are fixed. So the first one, like always, will be top level immune system. Then come to the second adaptive immune system. So it will be always the same. So it's good for comparison. And in the table view, you can do filter based on the p-value or based on FDR value. And then you can actually also click this. So you click this, you can go to Reactome pathway. Actually, there's some there's some kind of performance issue at the Reactome website this morning. So it may take a little bit of while to actually show the results. But usually it's much faster. So it's still loading. Okay, let me switch back. And another way is, so click this, you can see the results here. But another one is you can actually click this open in Reactome. If you click open in Reactome, you can get the actual Reactome's Illinois map that's shown here. For some reason, it's extremely this comes to the actual pathway. So here, so this is the individual pathway-based analysis. So you can see this is the results. So 2 of them are actually significant hit, and this one and this one. Just for time purpose, I will not actually show that. And this is, I said, is a Reactome Illinois view. So if you put a mouse here, so there are actually JavaScript-based impact view. Yellow means p-value lower, gray means like a high p-values. So each one you can double click and zoom in and then look at this. And if you click mouse and hold, so it will actually point to the detail in the pathway. So that actually is nice. It's all provided by Reactome. So that is a pathway-based view. So when this one opened, so the original gene expression analysis actually will be closed, but you can always open or close by yourself. So it is just a way to try to control the screen space. So if you want to do network analysis, you can just click this and look at the actual network. So this is also a JavaScript based, so you can really look at this one and put your mouse here and look at each genes. Okay, so that is for single view, but as I said, we also really try to do some comparison analysis. So in order to do comparison analysis, we can try to do another analysis. So just for demo purpose, I wanted to do another analysis between 7 days and 3 days. So this is 7 days and 3 days. So you can do same thing like analysis. So in case I will just do a pathway analysis, and it will actually show you pathway analysis results here. So after that, so basically we wanted to do comparison, right? So we want to compare results. So between 7 days versus 3 days, and another analysis, remember it's 3 days versus 0 days, and then click this one. So Since this is comparison analysis for gene expression part, so we have 4 colors right now. And another one is, actually, let me call this. Another one is pathway analysis. So for each section, for each high level, so we have A and B. So if you just wanted to focus on immune system, so you see, we basically can click this, double click this, and then click this, so select that. So if you put a mouse here, as I mentioned, so you can see here, interferon alpha beta signaling has much lower p-value, means much more significant at day 7 than at day 3. So by doing this, we can really see all these kind of longitudinally host response change. So I think I will actually stop here and move to Oliver. So thank you for your attention. I will answer questions afterwards.
Yeah, maybe we can take a quick question here.
Yeah.
So I will read the question. Is there a mechanism for updating with new studies that are released by ImmPort and GEO?
So far we have not really set up an automatic way to do that. So, but in the future, we probably will try to set up a pipeline to do kind of probably not really automatic, but at least a semi-automatic way to do updates.
So I also had a similar question where would it be possible that we bring our own data sets? So user bring their own data sets and then compare it with all the other data sets that's on VIGET? Yeah,
that's a great question. So unfortunately, right now the software cannot really support uploading users' data yet. But as a backup, and so we may be able to try to add some new features to do that. Because another thing I think one problem is right now it is still focus on microarray-based data set. So currently the majority of data obviously will be from bulk array or from single cell array data, right? So the comparison actually quite difficult to both computational biology perspective and actual data visualization are different skills. So we have not really tried to go to that every year. Yeah, fortunately.
Right.
Yeah.
No, this is great. I mean, this tool, like how much you could do with open access vaccine study data, right?
Yeah.
So maybe let's move on to our next speaker, and then if there are additional questions, we can again take it after the presentation. So we have our next speaker is Dr. Oliver He. Dr. He is an associate professor at the University of Michigan Medical School. His lab has developed and applied biomedical ontologies and tools to support data integration and sharing. And notably, he initiated and led the development of the vaccine ontology and violin vaccine knowledge base. Dr. He has collaborated with Dr. Guanming Wu for years and employing ontology-supported integrative analysis and visualizations to study vaccine-induced pathways and networks. So with that, let's welcome Dr. Oliver He.
Yeah, thank you very much, Sanchita, for your invitation for our presentation. So can you see my screen?
Yes.
Okay, so yeah, here I will be brief, basically to introduce one use case. So here is to study the yellow fever vaccines using the VIGET. And here we have 4 ImmPort studies imported. And they go around like day 0 to day 84 post-vaccination. So it's longitudinal study. We have 3 vaccines, YF, Vegas, Stamavir, and the yellow fever 17D. All the 3 vaccines, they are actually basically are all originated from the live attenuated yellow fever strain 17D. So the first two are actually trade names. So basically we can compare them at the same level. So we have collected 482 samples from the whole blood or PBMC, the peripheral blood monoclonal monoclonal cells. So for mononuclear cells, for the human subjects, it's 18 to 65 years old. So we have all like whites, Asians, African Americans, or females and males. So this is a very good story, and we think yellow fever vaccine actually has been a model for vaccine response study. So we think this is a good example. So we focus on the first 4 weeks post-vaccination. And our story focused on 3 immune systems: adaptive immune systems, innate immune system, and the cytokine signaling in immune system. So just to make it brief, so this one, Guanming has done a wonderful job to present the work. So basically, this one is more like an illustration of the conditions, right? So you have all the conditions here, but basically this one, like you can select this, and then you can select two, like for example, 2 groups, right? You can select studies, and you can define age or cell type. So you can do all this very conveniently. So it's a very user-friendly platform. So just give some brief introduction of the results. So here, like we generated a figure here to demonstrate the A and the B. So A is more focused on the immune response pathways and the cell cycle, and the B is focused on cytokine signaling pathways. So you can see here, the last one shows the different time, right? Like week 0, 1, 2, 3, 4 post-vaccination. So you can see the timely events. So you can see like some events, they are kind of updating, right? Up. Like for example, this is week 1, right? So I just give some examples. More examples can be seen from the letter. It's too small probably for you to see. So just give some example, like interferon alpha, beta, and gamma, and the innate immunity, like the neutrophil degranulation pathways. They are all like up-regulated. So it's 1 week. So you can see here. But then actually, there are also many down-regulated and up-regulated again. So it's a lot of details. Just for saving the time, I just go quickly. So this is another example. So it just didn't show. So this one is also 1 to 4 weeks post-vaccination. Some interesting observations here. Like for example, like the cell cycle. So you can see, right, this color means 2 weeks. So you can see the cell cycle actually is very low at 1 week and very high at 2 weeks post-vaccination, but then become low again at the 4 weeks post-vaccination. So it's interesting observation here. And then just give you another example, like the interleukin-10 signaling. So this is interleukin-10 signaling. So you can see here, the 2 weeks post-vaccination is very low, or you cannot see it. Right? At 4 weeks, it's very high. So you can see like clearly, there's some big differences. So just for a quick summary, the VIGET is a web portal to study vaccine responses based on Reactome pathways and ImmPort data. And we just use one use case to demonstrate how it works. Actually, my lab has been working on some other use cases. For example, we actually use a study to test the gender, the female and the male So we can actually find the female and the male. So basically, you can just separate the female, right? So you do once female, once male, and then you can get the compatible results. So when you compare them, we did the influenza, we compare a female and male, we found actually distinct profiles. Many pathways are different. So just because of time, and that's still unpublished data, we don't show it here, but I just want to indicate that it can be used for different use case studies. So another thing I want to say is because my lab has been focused on vaccine ontology, so it's great that ImmPort has been using vaccine ontology IDs to standardize the vaccine information. So actually, just with the IDs, right? So we have tools like OntoForce and some other tools like a robot developed by another group. So you can use many tools actually to build up, just using the ID to build up something like this quickly. So you build up some outlier and you can open Protege. You can see, the different patterns. So I think it's one advantage of using ontology for the data standardization, right? Because there are a lot of background information you can automatically extract it using some tool. So just the future work. So one is like when you look for the ImmPort, right, you can see many resources. So with this presentation, actually because our research actually was funded by ImmPort associate grant for 3 years. So we actually hope that our tool can be part of the resource. Just it's more like a hope, a wish, yeah. And as mentioned in this today's questioning, right? So actually, so we don't have all most updated data. Our data was more like last year, sometime last 2022. So in order to automatically including more data and in timely effort, the current mechanism is not working yet, but potentially in the future it's possible. So, and also we're trying to bring our tool into more use cases, not only by us, we wish everyone in the community using the tool and test out and let us know. So we also look forward to more collaborations with ImmPort and with our any interesting users. Yeah. So again, the primary is funded by the UH2 funding by both Guanming and me, and we have also got some other fundings, not directly ImmPort, but actually also vaccine-related one. Those fundings continuously being available, and we're trying to continue the work. And we like to thank many people from our lab and from our Wu's lab, and our consultants, Najee and Anna Maria. Thank you very much.
Yeah, thanks, Oliver. Any questions? Okay, so I have a question about, like, it's so impressive that how you downloaded all these studies from ImmPort. So my question is more like data curation, and then and I understand and how much it takes to download the data, then you do the cleanups, curation, and then get to the analysis or build a tool like this. So can you share your experiences, like when you were downloading these data sets? Was it that you downloaded all of the vaccine studies at once, or were you using the API? Can you throw some light there?
Okay, yeah, I can speak first. Maybe Guanming can follow with any additional one. So basically, our experience is ImmPort is a great resource. So ImmPort does not usually include gene expression data. So gene data, you need to go to GEO, but ImmPort provides wonderful annotations. So we usually go to ImmPort first and get all the annotations, like for example, the vaccine, right? You can get all the vaccine ID exposure information. And then once you get there, actually, then you use the information from import and then go to GEO. Actually, we had our automatic pipeline. So once we clean up from import, we can automatically download data from GEO. So the whole pipeline actually works very well for us.
All right, thank you. Yeah. So let's give a big round of applause for Dr. Wu and Dr. He, and thank you everyone for your participation. I'll just take a moment and just show the things that we do at ImmPort. So I'm sure some of you are already familiar. We have multimodal data across various diseases. If you have any disease of interest or conditions of interest, please go and check out ImmPort as immPort.org. We have, there is an ecosystem where we have a data sharing portal. We have a portal that's more a private data space for data submitters or potential data submitters who would like to share the data through ImmPort, data analysis, and other resources. Let's say that you are interested to know how we do all the data processing or the tutorials to learn about data sets. Go to the resources page. There are tutorials available that you could try out and to see how you can basically call the data from ImmPort database, and these are all Jupyter notebooks, so you can then combine the data sets of interest and do some data analysis. So this type of tutorials helps you get started. If you are interested in data science, stay tuned for future webinars. We try to host in the quarterly basis. We try our best. So next one could be coming up in fall. And also, if you are interested that what studies are getting shared through ImmPort portal, since we share the studies on a quarterly basis, feel free to subscribe to our newsletter or stay tuned going to the websites, and we have announcements through the social media about the data sets that we disseminate through the data portal. So with that, again, I'll thank for your participation and look forward to seeing you in future webinars.
Thank you.
Thank you.
Thanks, everyone.
Bye.